Hey everyone, welcome to my session. I hope everyone has got a good time at the summit so far. And just to introduce myself again, I'm James Lee. I'm a data advocate and partnership lead at SuperBI. I'm also the chair of this virtual summit, the Mislabel Virtual Summit. And the title of my talk is Enabling Data-Centric Computer Vision by way of DataOps. So if you are interested in concept like DataOps or computer vision in general, I'm sure you're gonna learn a lot from this session specifically. So the terminology, I call the term data-centric computer vision actually as an inspiration by the movement of data-centric AI. So just a little bit of context. So data-centric AI is this process of building and testing a system by focusing on data-centric operations rather than model-centric operations. And I would argue that there are many existing challenges with iterating on datasets in order to improve model performance. And therefore, there is an increasing need for DataOps for unstructured data that can systematically orchestrate data-centric operations. And then, some of these operations are things like data ingestion, data labeling, data QA, data curation, and data augmentation. And so the next slide is kind of my attempt to kind of paint a picture of how the DataOps workflow might look like for building modern computer vision application. So as you see here in the slide, there's a variety of different building blocks that we need to pay attention to when it comes to designing a DataOps pipeline and when you are building computer vision. The first block is data acquisition, which is essentially the practice of acquiring more data, right? So when we talk about data acquisition, we tend to think mostly about data collection, right? And they're both the physical and operation consideration with this. So ranging from where to collect the data to how much to collect initially. And if you want to get data collection right, you need a feedback loop that aligns with the business context. Synthetic data generation is the second approach with many use cases ranging from in facial recognition to life science to e-commerce and autonomous driving. However, getting this synthetic data requires many training data and compute. And furthermore, synthetic data is not realistic for some of the more unique use cases. And I think there's a lack of fundamental research on the impact on model training. And the third approach is known as data scavenging, where you can scrape the internet or use open source dataset like in Cargo or Google Search or any academic benchmark and use them for your development process. So that's all within the building block of data acquisition. The second building block is data labeling, which is an industry of its own because you have to answer so many different questions, like who should label the data, what data should be labeled, and how should the data be labeled. And indeed, getting this data labeling step right is extremely complicated because it is error-prone, slow, expensive, and often impractical. So efficient labeling operations could require a carefully vetted process, qualified personnel, high-performance tooling, its own lifecycle, a versioning system, and a validation process. The third building block is data debugging, which entails writing expectation tests to address some of the data preprocessing and start system. Essentially, these are the unit tests for your data. They're designed to catch data quality issue before they make their way into your DataOps pipeline. The fourth block is data augmentation, which is a scientific process where you can manipulate the data via flipping, rotation, translation, grayscaling, etc. However, there's still some fundamental issue that you can think of when it comes to scaling data augmentation to bigger datasets, negating memorization, and handling some of the bias and corner cases. The fifth block is data transformation, which included 3 separate steps. So we have data formatting, and this is a small slide of the whole data engineering task that interface with data warehouse, data lakes, and data pipelines. Feature engineering includes concepts such as feature store, management of correlations, management of missing records, and going from feature selection to feature embeddings. And finally, data fusion. This last step means fusing your data from different modalities, sensors, and timelines. The 6th building block is data curation, one of the most underrated steps in this whole workflow, because it bridges the gap between the DataOps pipeline and the MLOps pipeline. So data curation relies on this fundamental belief that because your dataset might be very large, you must be picky about the types of data that you're going to use. And therefore, you need to catalog, structure, and select your data methodologically. After data curation, you're going to have your MLOps pipeline when you perform all the model-centric operation, like model experimentation, model training, model deployment, and model monitoring, right? You kind of close the feedback loop of the whole MLOps lifecycle. Your system should be able to detect the failures and edge cases and use them to generate a new training dataset that can be fed into the next version of your system. And this block includes concepts and practices like drift detection, performance metric monitoring, and data observability. And so this is kind of like the conceptual framework that I been building via a lot of conversation with practitioners, as well as doing research on my own from in the past year or so. And so let's go a bit deeper and take a look at some of the challenges when your workflow do not have DataOps. Okay, so there are many different tasks that computation engineers cannot do well due to the lack of tools, time, and data. And so let's go through each of them and illustrate how DataOps can solve some of these issues. Okay. First one is data visualization and feature extraction. So on the left is your typical data set. You see there's all types of data with different colors, shapes, and background. Your task now is to turn them into the diagram from the right, which entails clean and cluster sample images. As an engineer, you're going to have to go through all these images, cluster them based on similarity, and then develop like maybe a machine learning model to do this task automatically. Essentially, you need to look at a lot of images and come up with feature ideas. Right now, this process is done very manually. Computer vision engineers have to manually visualize each image one by one, go through them with the human eyes, and repeat this cycle multiple times to come up with feature ideas. And I believe that the time, the engineers can really be spent on something else, not, this manual practice. Another thing that computer vision engineers are not doing so well right now is training dataset split and data curation. As a machine learning person, you're probably very familiar with this concept of, choosing and splitting your training and test set. Essentially, you build a model and train it on the training set, and then you evaluate your model on a holdout test set to see the performance of that model before deploy that model into production, right? So to illustrate with an example on the right, let's say if you only train your model on the top row right here and test it with data from the top row, then your model will only do well on this type of red cups, but it won't do well on the types of cups in the second or the third row, right? And that's why you need to train and test your model in a well-balanced dataset. But due to the lack of tooling, time, and data, computer vision engineers, at this point, just training model on the data with similar distribution, then randomly sample 10% from the training data, make it a test data, and test the model on the same test data. And a lot of biases and imbalance problem might emerge. And this is an example to illustrate that point about data bias and why data curation is important. This diagram here come from a curation report that our team Super AI has created. And this report is based on the BDD 100K dataset, which contains a lot of images and pictures being captured by a self-driving vehicle. Okay, so there is a huge long-tail problem, as you can see on the dark gray bar here, which come from the original random distribution of the objects. So examining it a bit deeper, you can see that there are so much more objects like car, traffic sign, traffic light, and person, rather than the rest of the other objects, right? So hypothetically, if you train your model on this randomly sampled dataset, your model will perform really well on the oversampled objects and perform poorly on the undersampled objects. The right side here is another example of gender bias. The cooking activity is associated with the woman Asian role, okay? And so the model has learned to identify a person cooking as female, even when the image is that of a male person. Then the final challenge I want to talk about is this concept of data-centric AI again. So just to kind of recap, data-centric AI is the process of building and testing AI system by focusing on the techniques meant to improve and optimize the data rather than optimize the model. And so broadly speaking, you can improve your data by doing these three things. And this actually comes from a very well-written blog post by the team at Alexio. You can modify your labels. Okay, so as I alluded in one of the earlier slides, labeling large-scale data is insanely expensive, time-consuming, and error-prone. Under certain conditions, it is possible to rely on a pre-trained machine learning model or weakly supervised approach to generate label faster. Additionally, you can use human in the loop, where human agent identifies and fixes labeling errors and imperfections. So that's the first approach. Secondly, you can also improve your data by modifying an existing dataset. So you can use technique like active learning to decide what data samples to be removed and augmented. And then finally, while this might seem quite obvious, another way to improve a dataset is to add more data, preferably in a strategic manner. However, guiding the collection or the generation of new data in a way that it positively impacts the learning process of the model and makes it more efficient is a topic that sadly does not get enough attention from researchers. And right now, due to the lack of tooling, time, and data, most computer vision engineers decide to tweak the models when their models underperform rather than tweaking their data, right? And so, given some of these challenges that we observe from conversing with a lot of computer vision practitioners in the past year or so, at Super AI, we've been hard at work to develop DataOps, which is an automated data QA and curation platform that empowers computer vision engineers and data project managers to explore, evaluate, and improve their vision-based dataset more easily, while reducing labeling, QA, and engineering spend. So the initial release of DataOps, which is still in beta, consists of the following AI-enabled features. So Mislabel Detection that can detect misclassified bounding box and segmentation annotation in images. Edge case detection that can find and mine the edge cases in datasets to prioritize for labeling and constructing test/training set. Auto curation that can automatically curate the test and training sets with matching their distribution. Image similarity search that can use embeddings to find clusters of visually similar images and objects within a dataset. Natural language query that can quickly explore and find needed data. Finally, an embedding store that can visualize your datasets in a two-dimensional space to better understand dataset composition and distribution. So I want to, double-click on 2 or 3 of, of the major features that being built in this release of DataOps, and then illustrate how some of these features can tackle the issue and the challenge that I mentioned in the previous slide due to the lack of tooling, time, and data, right? So let's take a look at workflow with DataOps. So to tackle, the first issue related to, feature extraction and database, with DataOps can leverage our embedding store and data visualization on top of that embedding store. So if you're not familiar with the concept of embeddings, is essentially a way to represent the information from a high dimensional space into a much lower dimensional space. And therefore, you can preserve relevant information about the sample while drastically reducing the cost of storing and processing that information. So, in other words, given a set of images, an embedding store can curate them into a format that the machine can easily understand and compare. So here in the slide, given a big cluster of images on the left, an embedding store can cluster them into smaller clusters of occluded images that are behind the bars, and images with various vehicles. So in other words, you can create embeddings for your dataset, look at different sections of those embeddings, cluster different images that you're looking for, come up with feature ideas, and then finally find patterns for your model development process. So let's take a look at a workflow with an embedding store, right? Here, let's say given a label dataset and you want to find, red cars at night. So you're going to apply a natural language query. Red car is the text and night is the images. And then put it into our embedding store, and then the store will perform semantic search, return you the results that you can check, and then you apply that new tags, red cars at night, into the resulting images. Okay. So what are some of the benefits of this new workflow with an embedding store? First, you can search, analyze, and understand your dataset better. Secondly, you can change your classes, a visually similar subset. So, for example, if there are cluster images that being already labeled as the car objects, right? Then you can select a police car, and you can find similar images, and then relabel that subset of similar images as police cars. And thirdly, you can add additional labels. Let's say, going back to our samples of the self-driving car dataset again, let's say that dataset only had the objects being labeled, but not the weather condition, right? So you can perform semantic search here, search for the term rainy, and then select all of those, and then add rainy, to as the property to all the images where the car is driving in a rainy condition. Okay. And finally, you can couple the embedding store with mislabel detection, which is another feature that I will talk about in the subsequent slide. So in order to tackle the issue with training and test set split, with DataOps, we have been developing an automatic curation feature. So in the beginning of your model development, you can split your dataset into training, validation, and test set. And similar to the test set, the validation set is split from the training set to track your model performance progress. So our curation feature deliberately split these three sets in a balanced way, as you can see here, even before you can start developing your model. So this is pretty important. So let's take a look at this diagram, which is another sample from our curation report. The y-axis shows the number of embedded clusters, while the x-axis shows the cluster size. The left side here contains the rare images, while the right side contains the commonly found images. So when you take a look at this dark blue bar, okay, and compare them to the red bars, you can see that the dark blue bars picks up a lot more common images. So if you train your model on these dark blue bars, which come from a randomly sampled dataset, your model will do poorly on the edge cases. So our curation algorithms is designed to pick up as many rare images as possible so the model can react and perform well on those edge cases. And this line shows another example of a curation report from the same BDD 100K self-driving dataset. For some of the object classes that are quite common, like car or traffic sign, there are not so much differences between the distribution of curated dataset and random dataset. You can see here, it looks pretty similar. But as you can see on the right side, bike and rider are the very rare objects in the dataset, and our current dataset picks out much more of these objects compared to the random dataset. And this is how we choose a balanced dataset for your model training and testing procedure. Let's review a workflow with data curation. So given a label dataset, and say you want to train your model for ABC classes and you need X images, right? You want to perform Data Curation, then you check the results, check your curation report, apply the new tags, then export those tags, and then use them export for your model development procedure. A couple of major benefits with this new workflow. Better distributed training and test set correlates with better model performance. You're gonna be able to leverage our automatic curation based on embeddings instead of relying on heuristic and manual labor. And finally, you can also tap on the power of our automated labeling capabilities. So our previous product, Super AI Suite, has a built-in feature called custom auto label that enable our users to automatically label the dataset in a matter of seconds. And by using workflow with data curation, you can curate a good training and test set to use for that automatic custom auto label capability. And finally, the workflow with DataOps. The last thing that I want to touch on is Data-Centric AI. And within this category, there's the two features I wanted to talk about is SK detection, mainly designed for more debugging, and Mislabel Detection, mainly designed for data QA. So SK detection is essentially an extension of our embedding store feature. After visualizing and finding different clusters with similar image characteristics, you can combine with another feature currently in beta that we've been developing called model influence uploading to see which clusters are performing well versus not well. So let's say in this example that I show here in the slide, the occluded images and the images that behind the bars are the edge cases that perform poorly based on our model results. On the other hand, our model seems to perform better on images with various vehicles. And so, with these insights, you can make intelligent decisions on what type of images to collect more. And additionally, we are also developing a semantic search capability. So in order to find more edge cases, you can feed them into our semantic search feature, which will discover images with similar semantic to those edge cases. And think about it, right? We'll keep feeding more edge cases into subsequent iterations of your model. Your model will eventually perform well on those edge cases. Now, Mislabel Detection is a feature for the data QA purpose. So it is an auto QA feature that automates the curation process to make it more efficient. Right now, it sorts the label data by auto mislabel score, and it shows you the images that are likely to be misclassified. And we are looking to improve this feature and iterate on it to provide you with more capabilities, such as fixing labels on the spot and putting those mislabeled images on a queue for labelers to review. And then another part of this feature is a mislabel detection report. And this report shows you the patterns in your data, such as the classes that are likely to be mislabeled, the visualization of different object classes so that you can curate them efficiently, and then based on the size and width of your data, how many mislabels there are for each aspect ratio. So you can use this information to fine-tune your labeling guidelines and understand your dataset better. So let's take a look at the workflow with mislabel detection. Okay, so first you're going to divide your label data into query sets and reference sets. And then you can export both of these sets. And then you're going to run mislabel detection on them. You check out the results, you check out the mislabel detection report, and then you choose the classes with high likelihood of mislabel. You apply the tags, and then on the label page, you can assign them for relabeling. Two major benefits with this new workflow. You can reduce the manual review and QA time and money. And then you're going to be able to obtain high quality dataset with fewer mislabel, and therefore reducing the chance of bad model performance caused by mislabel data. So yeah, that's sort of the end of my presentation. If you curious and want to try out our DataOps platform, you can join the waitlist for it in the tiny URL link that I put here in the slide. And then if you have any further question about just in general about modern computer vision stack, AI infrastructure, MLOps, Data-Centric AI, and kind of like how do you find communities that can talk about them, feel free to reach out to me at the work email address that I put here in the slide, and I would be happy to chat and kind of learn more some of the ideas that you have and group to brainstorm and ideate on how the future of MLOps and computation can look like. So yeah, I really enjoyed this giving this presentation, and I hope you learn something insightful from my talk. Thank you.